Ho, ho, ho! Merry Christmas. This is Santa Mike welcoming everyone to the Oklahoma City Astronomy Club's December meeting. We're holding this meeting virtually instead of our normal practice of having it at a Christmas party at the Science Museum, Oklahoma. We want to start off by wishing everyone a happy holiday season and a safe holiday season. And remember, be on Santa's good list and wear your mask. Even Santa wears a mask. And we have these dandy Oklahoma City Astronomy Club and Okie-Tex face masks, and Danny will tell you how to get one. And here's a reminder that the next couple of days will be the Geminid meteor shower. I think the peak is supposed to be Monday night. And in December 21st will be the conjunction of Saturn and Jupiter. So get out and look up. But I must dash away. Merry Christmas to all, and to all, here's Danny.
Hey everybody. Hope you enjoyed our visit from astronomical Santa Claus there. My name is Danny MacDonald. I am the newsletter editor of the Oklahoma City Astronomy Club, and welcome to the December club meeting. Obviously, we're still doing these virtually. This was supposed to be our Christmas party. Obviously, that's not really a thing this year, but it is super great to see everybody in chat. And we've got a great speaker tonight. We've got a stellarium show that we're going to do. We've got some announcements. Chuck, our president, is here with me. He is going to be on in just a second to say a few words. We are going to do things a little differently tonight. We are going to have our speaker presentation sort of up front, and then afterwards we are going to do our stellarium show. So hang in there. It'll be a great talk, and let's get this going. So, first up are some announcements. We still don't really have any sort of public outreach going on because of the coronavirus. Stuff is locked down and weird, and we still don't want people to be up close and like putting their eyes on our telescopes and like breathing into our stuff and that sort of thing. So for now, there's still not a lot of public events that are going on, but you know, the weather is going to start to get cold anyway, and there usually is not that much going on. However, the Cheddar Ranch Observatory is still available. If you don't know what Cheddar Ranch is, it is our private observatory about an hour and a half outside of Oklahoma City. If you are a club member, then you can go out there about twice a month, including tomorrow night if the weather cooperates. And if not tomorrow night, then we'll try again next Saturday. If you want to go and you've never been there before, then you should go to our web forum. Sign up for our web forum, and there will be a discussion thread there that will tell you all that you need to know about getting an escort and what to wear and what to bring and all of the protocols to be aware of there. So again, those two dates, if you want to go out to Cheddar Ranch, are tomorrow the 12th and then the 19th. Big in the sky this month, the Geminid meteor shower is gonna peak in the next couple of days, so be sure to get to a dark site like, say, Cheddar Ranch. if you want to check that out. And towards the end of the month, around the 21st, will be the conjunction of Jupiter and Saturn. A bit later in the meeting, I am going to switch to Stellarium and show you all how exactly you can see the Geminids and see the conjunction of Jupiter and Saturn. Now I think I will throw it over to Chuck, who can say a few words for us. Chuck, are you there?
I am here.
Hey, well, the floor is yours, buddy.
Hey, Merry Christmas, everybody. Happy holidays. Glad to be with you. Me and my buddy Oscar here. Yeah. So we're all in the holiday season and wish we could get together for the Christmas party. This happened last year. We had a delayed Christmas party in January, so I think this year we might have a party in May or June, and that actually might turn out to be better. So want everybody to stay safe and just be patient and wait for your vaccinations and things like that. Again, everybody be healthy. So when we have the conjunction star party, that's fine. If you want to get together and view it with your friends and whatever you organize, but let's not make it a public event and have a lot of public outreach for that just yet. There'll be plenty of time and plenty of opportunities for that in the spring and the summer. A lot of exciting things going on this December and this winter season. The Geminids, the conjunction, everything else that's going on. Even a snowstorm on Sunday in Oklahoma. So we'll see how that goes. But I won't keep you too long. Just to say that I really do miss everybody. I like the social interactions that we have. I want to say, we'll get to announcements later on, but there's been a lot of hard work from the club this year, the board members, the club members, whether it's planning for Okie-Tex and then having to cancel it, the new building project at Okie-Tex, working on Cheddar Ranch, updating the facilities and the plumbing and the mowing and everything. So all of that is so wonderful, and I'm just so thankful to everybody that gets involved with the club. I can't thank everybody by name because I'll leave somebody out, but I do want to really give a shout out to Danny for organizing these virtual meetings, and he's been a real superstar in all of this. So everybody said good wishes to everybody in the club, and anyway, I'll catch you on the other side. So pleasure to have Tom speaking this evening. So yeah, look forward to all of that.
One thing we desperately need the answer to, Chuck, is how is the grass out at Cheddar Ranch? I saw Tim Livingston in chat, and I know that he's only here to find out how the grass at CRO is doing.
Well, I'm a little disappointed because I sprayed for sandburrs and the sandbur weeds have come back, but we'll try and do a better job next year. But that's okay.
All right. Well, thank you, Chuck. I wasn't really paying attention to what he was saying, so I'm just going to assume that he had nothing good to say about me at all. So let's get to our speaker. Tom Field is a contributing editor for Sky and Telescope magazine. Excuse me. He's been there for about 7 years, and he's going to talk to us about spectroscopy. He actually is the creator of a piece of software called RSpec that helps out with the science of spectroscopy, and he's got a really cool presentation about what that is, why that's cool, and why that's important, and how you can do it with your own equipment. Tom was actually supposed to speak to us at Okitex, but we all know how that went. His talk is about 45 minutes, and then we're gonna have some time afterwards for some Q&A. So if you've got questions, be sure to type them in chat, and I will do my best to read those out to him once his presentation is done. So please join me in welcoming Tom to our virtual club meeting, and I am very excited to hear this talk.
Thank you, Danny, and thanks for all the work you did in the background to make this all happen. You tech guys are always the unsung heroes, and also Chuck, because just making these meetings happen and getting the people and the speakers together and all of that really takes a surprising amount of effort, as I've seen from this side. But as Danny said, I'm going to speak for 45, 50 minutes and then do questions until somebody drags me off the stage and we don't have any other questions, whichever comes first. So let me share my screen here and we'll get started. Danny, we can see that prism there on the screen?
Yes, sir.
Good, terrific, we're good to go. I like your logo here, great logo. So how have we managed to discover so much about the universe when, you know, we even haven't left home, have we? I mean, just the distance we've traveled is virtually zero. Images of, we need Chuck, I think, maybe to mute. Images of the universe show 2 dimensions, and we can get fleeting glimpses of a 3rd dimension just, you know, during eclipses.
I did the virtual background. So
Chuck,
backed up a little bit. Yeah. I'm sorry.
Danny, can you mute Chuck? Thanks. And we can get a 4th dimension like this one. You can see it like up in the upper right-hand corner, some stars changing. So, you know, the time dimension. If we spread the colors out, we get an as-if 5th dimension. It's gorgeous. Aesthetically, just, it's beautiful. And these gaps in the spectrum are like a barcode. They reveal a lot of information about the sun as well as other stars. For example, their composition. And lots of other things. I'm not going to read these bullets because I'm just barely savvy enough a presenter to know not to read bullets. But I'm going to show you examples of these as we go through tonight. Now, first, a little bit of science just to get everybody to the same level. Sir Isaac Newton discovered that we could split white light through a prism and get its component colors. You can also split light just by bouncing it off a finely lined surface, or even going through a piece of glass that has fine lines. And we'll see an example of that in just a moment. Bunsen, and most of us have heard of Bunsen because of his Bunsen burner. You know, he invented the Bunsen burner here to burn a sample, put the light through a grating, and then look at the result over here. And he was a real pyromaniac. He burned everything he could find. And the great thing is he kept great records, really good records of what he saw. And those records really served well in the decades following, as well as literally the centuries following. This guy Kirchhoff was a contemporary colleague of his. We're not going to talk a lot about him tonight, except just one thing on this slide here. I wanted to point out, you can see over in this upper right-hand corner example that we've got, you know, just the standard rainbow, Roy G. Biv rainbow with gaps. But then down here, we've got a different type of spectrum. It's more or less a dark background with dark lines. Now, which one we get depends on things we won't discuss tonight. But what's interesting is that whether it's a gap or a bright line, they're all in the same position. And we'll see examples of both those tonight. And actually, I did want to say one more thing about which one you get and why. It has to do with the temperature of the gas that the light is going through and things like that. I think one of the things that is surprising to people is how little astrophysics you really need to know to have a lot of fun in spectroscopy. I mean, I couldn't explain in great detail a lot more about these lines, but I know enough that I can navigate and get around. You know, I used to have a slide just before this one where I would list all the things, all the bullet points that I wanted to make in the talk. And I realized nobody wants to see 10 or 12 bullet points, you know, too many words on a slide. So I've come up with this new scheme. So I've got this little bell here that I can ding. And that means this is one of those points that used to be on that bulleted slide, but I've spared you. But it means listen up, because this is something that I felt was important enough that I wanted to highlight in the talk. And one is what I just said, and that is you don't need to have a PhD or an undergraduate degree in physics or astronomy. There's not an enormous amount of highly technical information that you have to know. And I think there's a myth people think there is, and there's just not. So you can see that each element has its own spectral fingerprint. For example, that reddish line there in hydrogen just doesn't appear. If you were like to go to the flower shop and fill a balloon with helium and then burn it safely, of course, you wouldn't see that line because it's not part of the helium fingerprint. In fact, hydrogen is so common in the universe that we actually have named the lines. You can see there hydrogen bomber lines, and each line has its own name, just a Greek letter, like we number the stars and constellations, or we name them by Greek letters. So let me first of all tell PowerPoint here not to hide my arrow. Here's the deal. Here's something that really bugs me, if you must know. And that is, you can see my cursor already disappeared again. Microsoft forces me to do this every time I start a show. It's like, get with it, Redmond. In fact, I was over there today. I should have literally, I was in Kirkland. I should have gone up to Bill Gates' house and knocked on the door and said, Bill, do you have any friends over there still who could make this a sticky setting so I didn't have to set it every time? Quick story about the Bill Gates house. This is a brand new to my presentation. This is unfortunately what free association will bring you. When he was building his estate here in Seattle, and that's where I am, a friend of mine drove over and parked in the back where the truck entrance was one evening. And he wasn't parked more than 2 minutes, he said, and a huge SUV with black and darkened windows, tinted windows, drove up behind him and just sat. So he felt he wasn't welcome, and he probably wasn't. Anyway, here is a periodic table, but it's got different information than the normal periodic table. Notice we've zoomed in on that hydrogen, and you can see there those hydrogen lines. That's the red hydrogen alpha. That's like robin egg blue. That's a hydrogen beta, and so forth. And notice there's a helium fingerprint, very different. This is just a different way I wanted to show you how unique fingerprints are what spectra are. So we don't have to burn things like Bunsen did. This is actually my software you can see over here. In fact, let's see if I can bring it up on my little stamp window there. Over here, I have a gas tube. Yeah, there it is. So that's a hydrogen gas tube. Let me turn it off so I don't hurt myself. This is, it's just like a fluorescent lamp or something, but it's got a gas in it. We've done some fun projects. I created this little camera a few years ago for physics, chemistry, and astronomy teachers. Same software. We've done some neat projects at the University of Texas and North Texas, as well as high schools. Some cool stuff you can do with this. There you can actually see the spectrum coming off that gas tube. There's a hydrogen alpha, that robin egg blue beta, and so forth. So far, everybody I've talked about have been old white men, right? Here's some examples of some people who aren't that. First of all, Annie Jump Cannon and her computers. These women were prohibited from accessing the Harvard telescopes. And so they ended up, fortuitously, for us anyway, but probably not for their careers, studying the glass plate, the film plates of spectra of stars. They were fantastically good at it and really, really bright. And with that understanding that they gained, classifying literally hundreds of thousands of spectra, they were able to come up with our star classification scheme that replaced all the former ones that just basically didn't work. Priyamvada Nataraja is at Yale, and she studies hyperactive black holes. Nancy Grace Roman was the first astronomer at NASA. She got her PhD in the late 1940s. She is a big proponent, you can see there, of the Hubble Space Telescope and helped make it happen, thank goodness. Elisa Quintana studies exoplanets and has discovered some exoplanets that are in the Goldilocks region around red giants, where they could have liquid water, which might indicate life or possibility of life. And Jedediah Eisler is at Dartmouth, and she studies, and pardon me if I look this up, supermassive black holes. And actually, I want to come back to Priyamvada. She studies, I've got my notes here, gravitational lensing around these black holes. The reason these are notes is I haven't used this slide very much. I put it together this summer. It's a fun slide to put together because there are just so many women out there who have done amazing things. We've gotten a little bit of progress in equality in the field. There's still a lot more to happen, and we're headed in that direction, hopefully. So what I'm going to talk about mostly tonight is this little grating here. It's a $300, $295. You'd think I'd know. I've only been selling them for 10 years. $195 grating. And it's 1.25" filter cell. And I think you'll be really impressed at what's possible. So this is one of those ding moments. It's cheap. It's inexpensive. Clearly, I'm not a good marketer, right? There's my website down there, by the way. But I think a lot of people think it's expensive to do this kind of science that we're going to look at tonight, and it's not. So there's lots of ways to use a grating like this. One is just to put it on the nose piece of a DSLR. You can see, for example, that's a little thread adapter we offer, and there's the grating. Just again, examples of just about every type of camera you could use. It could be a cooled FITS camera. There's also the opportunity to do, this is a video camera, one of those ZWO cameras, great cameras. And that's the R, and the R spec stands for real time, because with a video camera, you can actually process the video in real time. Even with a still camera, R spec can pick the images up automatically as they hit your, you know, I don't know what to say here. They don't hit your hard disk anymore. They could be hitting your solid state drive. That sounds sort of clunky. And then I thought, what about hitting your internal storage device? It's like, that's clearly not it. So in the lower left here, again, is an example of, you can't see it, but we've put a grating inside of the filter wheel. That works too. So you can piggyback a DSLR on your telescope, so you can multitask and do two different imaging tasks at the same time. Okay, so that's all the history, the theory, all that stuff. What can we actually do? Well, we take the star and we put a grating in the light path and we split the light. Some of it just goes straight through, because the grating is not 100% effective or efficient, excuse me, in bending the light. But some of it bends into this rainbow that we can capture on our sensor. So check this slide out. This is just gorgeous. It's done, notice down here, guy's name is Torsten Hansen, with just an 8-inch Newtonian and an imaging source camera. I'd forgotten I had it on the shelf here. They seem so clunky now. They're great cameras too. They're a little older than the ZWO cameras. But these are all different spectra captured. These are the hottest stars up here, the B stars, then we have some A stars, and then F, K, and M stars. So notice that those spectra are very different for different star temperatures. So again, ding moment, you can tell star temperature by looking at their spectra. Let's just look at two really quick examples. Down here on these, what are they? These cool stars, these type M stars. Notice these, well, they're not a single absorption gap or line. That's like a forest, right? It's called a band. The cooler stars have a relatively cool surface temperature. And as the light goes through, it's not so intense, it's not so hot to burn up more complex molecules than just hydrogen and helium, simple molecules. So these bands are typically from some more complex molecule on a cooler star, a cooler surface. In this case, they're titanium oxide. And I don't know much more about that, but except that we can use these to determine a little bit more about the temperature of a star. You know, I don't mean to sort of brag about being stupid. I am a knuckle dragging programmer. Freudian slip, it'll get you every time, won't it? So, but the ding moment here, which I mentioned earlier, and that is, you don't have to know all the technical background. I've been trying to think of an analogy. Today I was in the car, I was thinking, what's a good analogy for that? It's sort of like, you don't have to know, you know, the chemistry of a car battery to know there's a plus and a minus, to know that there's voltages in batteries and that you can charge them. So there's lots you can do without drilling all the way down to the atomic, subatomic, and quantum level. The only other example I want to show you on this page, and it's a pretty significant one in terms of importance. Notice that strip right down there. There's lines all over the place around 4800, and that's in the robin egg blue. In fact, these are the hydrogen beta lines. And notice that they're not the same width. Their prominence varies. So here's how this all works. Remember, the Bohr model of the atom has electrons going around in orbits. It's pretty straightforward. Bear with me here if you're not familiar with this. And here's an electron, and electrons sometimes jump up and down between those orbits. And when they do, they give off or absorb energy, which create these gaps or emission lines. And what color those gaps on depend on the actual element or chemical, as well as the jump. And this hydrogen beta here is the jump between 2 and 4. So these stars up here, notice it's not as prominent because these hot B stars, a lot of the electrons, when they get blown up to a higher level, just keep going because it's so hot. So they don't stop at level 4. So they don't get that transition. And on these cooler stars, a lot of the electrons just don't even make it up to level 4 when they get pumped up by the heat, by the energy. They just maybe go to level 3. So that's why these are dimmer. So that's the chemistry or the physics behind how we can tell something about the temperature of stars just by their spectra. Now, my wife always wants me to dress for success. I think this is the slide where there's the most color coordination. If you look down in here, not every head can do that, can they? Right down in here, there's a hydrogen beta or alpha, I guess. But I mean, here's the deal. It's sort of off the record. All of you playing at home, all of you at home like me, you've encountered what I'm about to describe here. And that is, if you go down deep in there, you'll see that, and we're all about color in spectroscopy, you'll see that it's no longer red. It's actually getting a little grayish, shall we say. And the salon, you know, I've had trouble getting in. Some of the salons aren't open. They were open, then they closed. So that little graying out at the bottom there, like I said, I think some of you at home probably have encountered this kind of thing, either with yourself or maybe somebody else living in your house. Just saying. So this is not what my wife meant by dressing for success. She doesn't beg me, but she strongly encourages me against doing this, but I persist. So look at that crosshairs right there. Maybe you can see a little dimming going on there. Well, suppose I got time on the Hubble Space Telescope. I studied some spectra and I tried to publish a paper. I wrote it and it said, we saw a little dimming in the robin egg blue. That's not science, right? That's just qualitative. To do science, we need to be quantitative. So it's pretty simple how we do it. We actually just graph the intensity. How bright is this area? So some of the starlight, well, for example, this star, it's very bright and narrow. So this is a very high peak and it's not very wide. Whereas this thing over here, right, it's pretty dim in that area and it's pretty dim there. And it's, you know, it's much brighter here because it's wider. That blue doesn't show up very well, does it? So this thing is, you know, intensity wise, it's dim, but then it gets brighter, and then dimmer, just like this up here. But look at this. See that dip in the red on the right? Even though we can't quite see it visually with our eyes, which is, I suppose, the way most of us, all of us see things, the dip is very clear. Now we can do science. We can measure the width of it, the location of it. How's it look on other stars? How's it look on other telescopes and cameras? What's it look like on this star tomorrow night? How's it look like on the other side of that galaxy? You look at the two wings of the galaxy, maybe they differ because, hey, maybe galaxies rotate. That's science. So how do you get that graph? Now, my story is I got a grading in 2009. I went out with my C8 right outside here, outside my backyard, 3 miles from Pike Place Market here in Seattle. It was August. I came in at midnight. I had some video. I had it was like a Logitech webcam. I had it out on my bench here for a while. I don't seem to have it right now. I duct taped it onto the barrel of an eyepiece I'd removed. And I had some video. In fact, this is a freeze frame from that video the first night. At midnight when I came in, I had a sore neck. The knees on my pants were grass stained, right? Because it's Vega in August. What do you expect? And Sunday morning, I went to create this graph and I failed. I downloaded the freeware that's available and it was, it was crap. One wouldn't even install. It was DLL hell. And I think it was written for Windows 95. And they both of the programs were in French. They kept crashing. I was getting error messages. There's nothing worse than an error message that's in French. And then you click oui, or whatever the equivalent is okay in French, and the program just crashes. That's adding insult to injury. So what did I do? I gave up. I did. I really did. I told my wife, this is a hobby. I'm supposed to be having fun. I'm not. So, you know, I took the grading. I just put it in the drawer. But it kept bugging me. It kept weighing on me. And a few weeks later, I decided, okay, Saturday, I'm just going to write a program to create this graph from that spectrum. And it was from a video, and I had some rotation. I mean, there were a lot of challenges. Sunday morning, I had it done. I've been writing software since the 70s. So I wasn't quite in diapers, but almost. And software was done. And I hadn't thought to turn it into a product, but I eventually did, just because people liked it. Now, what, 10 or 11 years later, 10 or 15,000 hours later, the software is almost done. And my wife keeps saying, would you finish the software so we can have dinner at a regular time and early? It's done, but I like to share that our spouses are long suffering. So, you know, I think one of the obstacles we all face getting into some new aspect of astronomy or getting some new camera is, oh no, another learning curve of software. This is definitely a ding moment. So, because, I mean, unless you're a masochist, learning new software it's a mix. It's not all bad, but it's certainly not all good either. So I'm not going to give you a software demo tonight because I know better. I know it's after dinner there, and you know, if we were in Zoom and you had live video, I'd be beginning to see the tops of people's heads as they fell asleep and snoring if they weren't muted. But I think it is important that you see how easy it is to do this stuff. So I'm going to show you in less than 10 clicks. This is a still frame from that first video I made. There's the star, there's the spectrum, there's a gap there, there's some gaps there. Maybe you can see them on your remote monitor. So now you can use a color or a mono camera. A mono, as you know, we know from visual imaging, is more sensitive and a little more scientifically accurate, but I like color for outreach and education because it's so much clearer. So if you bracket in the area that you want to study, let's do that with these orange lines. Let's get it bracketed in. Then you get that intensity graph. I mean, that's literally how easy it is to get that graph. So this peak here is the star, and this area over here is that area, and that dip right there is that deep dip there, which happens to be oxygen in the atmosphere. Pretty neat, huh? So there's a lot of dips over here. Big effing deal, right? So what? They're dips. Now what? You know, Tom made it look easy, but how do I interpret the results? Remember I mentioned that Bunsen burnt everything and kept a really great catalog of all the different spectral fingerprints he saw. Well, they have now, let's see, not his catalog, but the grand catalog, still in use today. So we can actually, God, excuse me. How rude, my apologies. So there's a catalog. We can come down here to Hydrogen Bomber, and on the right, you can see over here an overlay template that's showing where, if we were seeing the effects of hydrogen on the star, we would see dips. And if we zoom in, we can see they correspond to our data. So we have compelling evidence that here with an 8-inch SCT and a Logitech webcam, we can detect the absorption features that occur as that starlight leaves the star and goes through the helium in the outer shell. That's pretty cool, isn't it? So I want to show you one or two other quick things here. One is, I'm going to turn off the fill here. I'll leave it on for a second. This is actually a video. Let's play the video. Now, over here, we can see things jumping around because my seeing was changed. It was pretty bad. It might be rock solid if I was shooting this at Okie text, but over here, things are jumping around too. Now, you know, we've all heard about stacking and, you know, how you can add images to eliminate noise. Let me remove that fill for a second because I want to show you something pretty cool. Right here, you can see coming and going. There is a dip, an absorption feature, but it's not very stable, is it? It's jumping around. If you didn't know to look for it, occasionally, if you were looking at the right time, you might see it. I'm going to turn on stacking that's in the software. Watch how quickly 1 Mississippi, 2 Mississippi, 3 Mississippi, 4 Mississippi, 5 Mississippi. So 5 seconds at 2 frames a second. And we have a really nice, stable spectrum. Pretty cool, huh? So that's what stacking does. That's really all I wanted to show you tonight in the software for now. If you would, as we leave here, in your mind's eye, if you could just remember that view, mainly that we've got a spectrum, it's Vega, and there's some dips. And the main thing I'll be calling out later are these reference lines, this template that we use of the hydrogen bomber series in order to identify things. Okay, let's get back to the stuff that is here. And let me come back one more time. There we go. Here's a star party. You know, that screen I just showed you in the software, it's a great outreach tool. I saw some cool still shots at the before the YouTube live transmission started of 3 fellows and their telescopes sitting on a grassy kind of garden edging. It looks like you were all doing some outreach, and this is a fantastic outreach tool because again, it's colorful, it can be moving, and it just captures people's attention, and it gives you a platform to transition into talking a little more science. So this is definitely a ding moment, because not only can you use it in outreach, but once you've spent, a few weeks reading and doing a little bit with the star analyzer grading, actually, it really isn't much longer than that because you're bringing your background to the topic already. You can actually go to a science teacher and say, hey, look, why don't we do a star party for your students and we can actually really talk science? Astronomy, chemistry, physics, they all want to know this stuff. It's all part of the sciences. And it gives you an opportunity to mentor. You can actually, the nice thing is you can choose the cream of the crop, or the teachers that will do it for you, and work with students and your telescope and actually do a science project, simple science project. Okay, let's move a little more quickly here. Here's a wide field view, again, of some stars with a DSLR. There's the stars, there's their spectra, there's some gaps. Down here, here's a star with some lumps in its spectrum. Those are emission lines that have saturated our pixels. In fact, let's look at a Rea Star here for a second. So I have a true confession, really. I have that confession to make, and that is when Janet Simpson sent me this about 10 years ago, I couldn't remember what a Rea Star was. The thing is, we've all read about Rea Stars for years, but it goes in one ear and out the other. A Rea Star is a late stage star. Wikipedia is my friend here. And it's very hot with intense stellar winds. It's starting to dissipate its outer shell. So we have these emission features out here. And here we can see carbon, carbon, carbon. Why would we see carbon on a star? Well, remember, the process of a star burning is a fusion through the elements. And during that process, CNO cycle or whatever, you have carbon involved. And that's what we're seeing here with a DSLR. No big telescope, just a DSLR and tracking. Pretty cool, really cool. Let's look at another emission. Oh, I was going to say ding moment here. And this is really, in my mind, one of the more significant ones. And that is when you get your hands on the data, your whole relationship to it changes. Now, not only are you interested in digging down a little bit and reading about it, but you have this, I hate to use big words because I'm not a big word guy, but you have this cognitive sort of infrastructure in your mind on which to hang those concepts. I sort of look at it like it's a hat rack. And then when you read about Rea Stars, you might remember more than you would otherwise, which is doesn't take much since I remember so little from the past. So here's our beloved ring nebula. You can see 2 emission lines, hydrogen alpha and ionized oxygen. That's what that Roman numeral 3 means. It's just some electrons have been removed. Emission objects with a grading like this don't really generally look all that interesting. M57 is the only one that does, because the object is extended. If you want to look at extended objects or go higher resolution, then you go for a slit spectrometer. You can see they're like an order of magnitude more expensive, and now you're guiding through like a 10 or 20, 30 micron slit. It's a steep learning curve. Almost nobody, I mean, literally almost nobody, I'd say 1 in several hundred starts with these. Pretty much everybody starts with a inexpensive low resolution grading, which can do some science that these can't do too, and that is get a wide field spectrum, a broad spectrum. Here's M42, beloved, as it is. You can see here's a emission line. There's our ionized oxygen with the Roman numeral 3 and hydrogen alpha. Notice how these are very narrow, even though this clearly is an extended object. Quick story here. When I'm doing presentations live in Zoom with people in Zoom, I sometimes will stop screen sharing for this. And that is, it's fun to remember when you didn't know something before you learned something, because you learned something about how ignorance works and how learning works, all those things. Useful to know, useful to understand. So in 1990, early 1990s, Shoemaker-Levy was coming. I didn't have a telescope. I didn't know anything about it except I'd seen beautiful pictures in the magazines sometimes. And I was almost going to say the web, but I don't think there were lots of beautiful pictures on the web back then. I know there weren't. And so I went out to the Denver first quarter star party downtown. I saw it advertised in the paper or something. Got out of my car, parked my car, got up on the little hillside on the curb and looked down at the observing field. And what I saw, those cannons that they shoot people out of at the circus. That's what I thought I was seeing. They were Dobbs, I know now, but I didn't know them. And I'm thinking, WTF, what's the circus doing? This doesn't compute. And like I said, I knew they eventually understood they were Dobbs. I queued up. Somebody, much like some of you or me, was running the Dobb. They were all excited to show us M42. I got up to the eyepiece, and sometimes when I'm in Zoom, as I started to mention, I'll stop screen sharing and ask people to tell me their story the first time they saw M42. And what I'm fishing for when I ask that of the group, and I sometimes get the answer I'm looking for, other times not. I'm looking for somebody who says, what pretty much was my experience, and that was, it was a smudge. It was a boring mono smudge, like a cloud, because it oftentimes is. Sometimes I get guys who go, oh yeah, the first time I saw M42, it's on my 24-inch Dobb. It's like, what? I don't want your story. It's a great story, but it's not my point. The reason I tell this story, silly as it is because if that was your experience, much like me, I'm sure you still go back and look at M42, even though it was a disappointing smudge. Why? Well, of course, we've got better telescopes, we've got better observing sites, and we've also gotten better at remote averted vision. We can, see things with the, averted vision, so, we can see dimmer things. But here's the point of this whole story, which is far too long for the time we've got allocated tonight. And that is that when we understand what we're looking at, which you do now when you look at M42, right? It's a birthplace of stars, stellar nursery. When we have that understanding and come to the eyepiece, our visual experience gets that much deeper. And that's what spectroscopy has done for me, is I understand a little bit more about what I'm seeing visually because I've seen plots like this and because I've asked people on forums, what's the meaning? Why is there a helium line there? So I just wanted to share that. You heard I rang my ding bell pretty loud because that is one of the most meaningful aspects of spectroscopy is the understanding it has brought me. So here is Uranus and Neptune. You can see at the top, there's a spectrum. This is done by Torsten Hansen, again, with that 8-inch Newtonian and a video camera. You can see a deep dip there from that band. Oh, what do we know about bands? We know they're from cool objects and they're produced by complex molecules. What kind of complex molecule might we see on Uranus and Neptune? Well, how about methane? we're seeing with a backyard telescope the methane atmosphere of a not a star, of a planet. Of course, when we discover, if we discover ET, it is very likely, not assured, that we would discover it by spectroscopy. We'll discover some gases, probably some bands just like this, even if we were observing, say, some planet like, I don't know, Venus, you know? We would see a band of something that we wouldn't expect to see unless there was life there, right? Like oxygen. Oxygen doesn't last very long. If you just pump a lot of oxygen into an atmosphere of a planet and sit and wait a while, there's not going to be any more oxygen after a while. It falls apart. It combines up. Whatever it does, it's not there. So if you find oxygen, you know that there's been something producing oxygen recently, relatively, and that, as far as we know, at least in our example, some sort of life form. Okay. So in what, 1881, Henry Draper, that's the Draper catalog guy, observed a comet. Hank can do it, heck, so can we. Here's a comet spectrum. You can see this string of jewels here. Over here, we can see the swan bands, carbon bands. This was captured by Vikram Agnihotri. He's a nuclear power plant engineer in Northwest India in Rajasthan. In 2013, he was a bare newcomer. Today, he's an expert. In fact, I learned from him, and what teacher doesn't like to learn from their student? Interesting guy. So here's a more contemporary example. We can see Neo-Ys, and this is the sodium of the tail, done with just a star analyzer in an objective grading configuration. It's not worth dragging my camera out, but that's when you just put the grading right on the lens cap threads. So, you know, anybody who uses a C-clamp as part of their setup, that's my kind of guy. The problem is I break everything. So if it was me, I would be cranking on that C-clamp, and then eventually I would have collapsed that video camera housing. Fortunately, Robin Leadbeater didn't do that. He's the designer of the star analyzer. He put one on the lens, and he captured this spectrum down here. That's the actual meteor, Perseid meteor. This is its spectrum, and that gap right there is that dip of a Perseid. It's a relatively rare branch of spectroscopy. There's lots of challenges to it. Not that it's hard, but you got to wait a while. And yet everybody chooses what they want to do, you know, whatever floats your boat. So we're not going to talk a lot about the sun spectrum, except that with just a simple setup, you can capture the spectrum of the sun. And that's where we discalloped helium. Discalloped. That's a great word. That's where we discovered helium. So if you do novae, if that's your thing, you'll see some novae have an iron absorption feature there, others don't. Quick review on Doppler shift. It's the pitch change that like a car horn makes if somebody's, you know, holding down their horn as they go past you, right? Right? High, high, high as they're coming towards you, low, low, low as they're moving away. So it's lower when it's moving away, it's higher when it's coming towards you. Same thing with light as well as sound. So if we were expecting to see this triplet here, and instead we saw that triplet over to the side, we'd know that that object was moving away. It was redshifted. And if we saw the triplet over here, we'd know from the blue shift the object was moving towards us. Let's look at a quick example. So there's a particular type of supernova when a star explodes called a type 1a. And this one has a, I love this expression, binary pair. Wouldn't that be 4 stars? A binary system, a pair of stars. And some of the gas from the larger star ends up on the white dwarf smaller stars. And when you pour gas on a hot surface, you get an explosion. So here is a supernova type 1a in M101. There's what another type 1a supernova, not this specific one, but one in our galaxy looked like. See, you sort of see the spherical shell. Can you see that? There's a spectrum captured by David Strange with just a 9-inch SCT and less than 15 minutes worth of stacked images. There's the spectrum, and there's a deep dip. Barely see it there, but it's clear there. Now, this is really cool. You know, we say we stand on the shoulders of the giants. Look what the giants figured out. The giants figured out that there's different types of supernovas. Some are just when for example, a star runs out of fuel and collapses on itself. But this type 1a we saw is this pair of stars, and notice its spectrum has this deep dip in the blue at around 6,000. That's silicon. None of these others have that deep dip there. That's a fingerprint for a supernova. And this is the kind of thing that we can do to help the professionals. They would like our help classifying supernovae, and we can do it. The only challenge is that they're often pretty dim, so we need a fairly large amount of aperture. But check this out. David and I noted that that wavelength of that dip there was 6150. So we noted that down, and we looked up where, if Bunsen had burnt beach sand in the lab, he would have seen an absorption line there, stationary. Now, I couldn't remember the Doppler Shift formula, but, you know, Wikipedia is our friend. I looked it up. I plugged the numbers in. We have now calculated the velocity that that shell is coming towards us by virtue of the blue shift of that feature with a backyard telescope. So Adam Rees, you may recall, won the Nobel Prize for work he and his team did just before the turn of the century, studying the accelerating cosmological expansion. And guess what type of star he often used as a standard candle? Type 1a supernovae, like what we're observing here. So somehow I don't think he used a grading like this. His equipment was a little more expensive. But in bang for buck, we do pretty well here at just $200. So what about the spectrum of a black hole? Well, of course, a black hole doesn't emit light, but the accretion disk, as it's spiraling around and in, gets very hot and has an emission spectrum. David Strange captured 3C273 and the spectrum there. You can see two little dots at the top of those right arrows there. There they are blown up, and there's the spectrum. This guy, Martin Schmidt, now in a live meeting, I especially if I'm in person, if I'm ever at Okie or when I've been speaking to a group in an auditorium via Zoom, I'm always looking for some kid, not to pick on them. I make a point of assuring them I'm not going to call on them, but so I can point out that this guy was probably just 10 years older than that kid. This guy was 25 when he looked at this spectrum and he couldn't figure out what those peaks were. And he said, okay, I'm going to, you know, like a lot of science, let's eliminate things that those peaks are from. So he said, let me just first of all prove they're not from hydrogen. So he brought up the reference lines, and this is that screen in my software I asked you to keep in your mind's eye, mainly for those reference lines for the hydrogen bomber series. But he said, they don't line up, do they? They're all right. I've eliminated these peaks being from hydrogen, except they were, and he figured it out. And, you know, in hindsight, it's like, oh yeah, they're just shifted. So they are shifted by cosmological expansion. So he went home that night and he told his wife, honestly, there's a great interview with him. I'm happy to share with you if you ask me on our contact form on our site, listed at the bottom of the screen there. He went home to his wife and he said something terrible happened at the lab today. Terrible? Why would it be terrible? Because he really anticipated the fame he was going to get from this. And he didn't want fame. He wanted to do his work. So we are able to calculate with our backyard telescope the redshift for this quasar, which allows us to figure out how far away it is. The discovery was that it was so freaking far away that we really shouldn't have been able to see it unless it was unbelievably bright. How bright was it intrinsically? Two wonderful examples. One is it would have to be brighter than 100 times all of the stars in the Milky Way. That's bright. And the second example is if it was as distant as the star Pollux, and you know, stars are pretty far away already, it would be almost as bright as the sun. That to me really strikes me in my gut. It's like, oh, these things are bright, aren't they? So, you know, the amazing thing for me is that this light, which is 2 billion years old and has traveled such an enormous distance, still has enough information in it that we can learn something about how that object was 2 billion years ago. That light as if didn't age, it seems. Now, things here on Earth don't age quite as gracefully. There's Martin Schmidt a few years ago. And listen, I've been rightly, justly accused of throwing rocks at a house of glass, right? I mean, he's got a full head of hair. I don't. That's why I'm poking fun at him here. Two more quick examples and we'll figure out. So far, we've been looking at features like these. They're not very wide. They're less than 15, about 50 angstroms wide, maybe. If we wanted to look at the details of this hydrogen alpha feature, wouldn't it be great if we could just zoom in with our mouse? Doesn't work that way. As you know, it's like putting more and more magnification. I'm looking for an eyepiece to wave around in front of you, but I don't. Oh, here's one. You know, you're looking at the moon, you go, I want to see that crater even more big, more clearly. You put more magnification in, what happens? After a while, nothing. It gets bigger and equally indistinguishable. So empty magnification, that's what the mouse roller wheel would do. Then we need, in order to drill down into these details, we use a slit device like I talked about earlier. So there is that feature on a slit device. And like we do a lot in science, let's compare Vega's hydrogen alpha to another object, say the moon. The moon isn't moving towards or away from us appreciably. Let's look at its spectrum. Oh, look, it's different position. That shift, that Doppler shift allows us to measure the radial velocity of Vega. It does take a slit spectrometer, but we can do it. It's pretty amazing. Last example, and for this one, I do need, I have here a little visual aid. It's a spinning basketball, right? I mean, a spinning star. So this edge is coming towards you and that edge is moving away from you. So if we look at the graphic here, the edge that's coming towards you, the light's blue shifted. The edge that's moving away from you, the light is red shifted. Let's look at the spectrum of a rapidly rotating star and compare it to Vega that's not rapidly rotating. Ooh, look at Altair. It's really broadened, and why would that be? Well, because some of the light that would be in this area got shifted blue and red. The giants are brilliant, and we're brilliant. They, both the men and the women, were able to figure out amazing stuff with such simple gear. Now we can reproduce some of those results. So let's real quickly look at what it takes to get started. I've already mentioned the star analyzer for about $200. Most any camera, like I said, color, mono, cooled, DSLR, whatever, video, static. My software, this is the freeware I've mentioned earlier. It's gotten better, still quite a challenge to many people. And you may need a spacer, and that's because this distance isn't critical, but it has to be within a certain range. And so sometimes you insert a spacer here, and there's a little calculator on our site where you plug in your telescope and camera specs, and you look for some green flags over here. Oftentimes people just send me, they click this link and send me their camera and telescope, and I tell them which of our gratings they need, and if there's, they may need a focal reducer. It's just hard to tell without the calculator. So there's lots of interesting books out there. I wanted to mention this one real briefly. All the books are shown on my site under links. This book right here is really spectacular because it's got these cool images which show you what you're looking for. But even more exciting, and this is amazing. I haven't given a talk in about a week, so everything got put away. So here's the book, and the reason I wanted to drag it out to show you is that in addition to those samples of what you should see, they have all this really great text that explains what we're seeing. And it's not written for PhDs, postdocs, or professionals. It's written for people like you and me who are learning. So, there was a ding moment I actually overlooked, and it would have been better to share in the beginning, because for those of you who are armchair astronomers, maybe you don't observe, or for those of you who don't do any imaging, it's just not your cup of tea. Still, understanding spectroscopy, what you've heard tonight, maybe even, I wanted to show you, one thing at a time. Still, understanding spectroscopy can deepen your appreciation of what it is we see, what it is we read about. And I was going to mention here, we've got a great forum with wonderful discussions, open to everybody. But what I wanted to mention was the software is free to download. For 30 days, you can use it. I gave a talk, actually an hour-long workshop to about 100 AAVSO members 4 years ago. And that was actually recorded and is up on YouTube. So with the free software for 30 days and the sample data that's there, you can actually follow along on YouTube. You could do this tomorrow, Saturday morning. You could download, hopefully you have 2 monitors, you watch YouTube video with me blabbering on about showing people how to do things, and then you actually do it on the other monitor. Within an hour, whether you never plan to use a telescope or do spectroscopy again or ever, you would have it in your bones. I'm sort of beating my chest, but you can't see it. I don't want to go like this because then somebody's going to think bonehead and they'd be right. So there are opportunities for pro-am collaboration. These are all amateurs here giving a presentation at a professional conference. Not as many opportunities as we'd like, but AVSO has jumped whole hog. Their current executive director, Stella Kafka, she's great. Her predecessor, Arnie, they're both professionals. They understand the importance of spectroscopy, that, you know, more than half, maybe 60, 70, 80% of the research on stars and galaxies, on astronomical objects, is done with spectroscopy. So the AVSO has an online database you can contribute to now, Spectra. So we've come a long way in the last, it's almost, it's not quite an hour, maybe 50, 55 minutes. I apologize for going over a little bit. We've also come a long ways in the last 200 or 300 years. We do stand on the shoulders of giants. The view's spectacular, if I don't abuse that metaphor too much. But I'd invite you to jump into the growing number. And frankly, it's no longer cutting edge. There are thousands of amateurs doing this kind of thing today. And with the web, it's easy to find somebody to help answer your questions. So I'm always available, whether in the next few minutes or via our site's contact form or email. I love answering questions. My real joy is helping people and seeing people do something new for the first time and just getting blown away. You know, it's like that first view of the moon that you got that just blew your mind, or of Saturn or Jupiter. It can happen again with spectroscopy, and it does almost every day around the world. Thank you all again. I'll stop sharing my screen, and I'll wait to hear what questions, Danny, you came up with there. Oh, okay, Scott. Hi. And it's a good question. Exoplanets are going to require one of those slit spectrometers. It's almost not possible by amateurs. Some of the most advanced amateurs have done it, but it does require a slit device. And, you know, mostly they're being done photometrically now, detecting exoplanets. But it's not impossible, but that would be a stretch goal for most of us. It's a good call. A good call, though. A good question.
Great. So I've got a question. So you mentioned at the end there the AAVSO, which at Okie-Tex, I think each year or every other year or so, we get a speaker and that comes and talks about variable stars. I think Dave Cotterill out of Canada is a mainstay at Okie-Tex, and I think that he speaks a lot about those. But you mentioned at the end that there was a database. So in my mind, that means that I can take my spectroscopy adapter, go out one night or over a week, take the spectra of a bunch of stars, and then upload to and then send all that data to this database. And then what happens then? Is there number crunchers there that like take all this data and do cool stuff with it?
That's a great question. Everything you described you can do, the answer is yeah, absolutely. You can capture spectra, throw them into software like mine, create an output file. They don't want the original image. They want just the graph, the intensity graph, and submit it. Now, what they're doing with that, it's sort of like what's happening with the photometry database, and that is professionals, sometimes after the fact, if there's been some event, may come to data mine and to look at those and compare and see what may have changed. It's a fairly young field right now in terms of the relationship between amateurs and professionals. There are pro-am collaborations going on today that use data from the AVSO, and there will be more. Most of them, I'd say 80% of them are using slit spectrometers and producing really high quality data that professionals love. And the good professionals, there's one in Italy, for example, he's an American named Steve Shore. He will actually produce little essays or give presentations, as he did in an AAVSO conference online last month. I was speaking at it also, but I don't say that to brag. You know, I'm here and he's like way up there. But he will lecture. He'll give a talk and go, here's why you're seeing the spectrum this way. So there's, in terms of getting educated as well as contributing, it's an excellent opportunity. I can see the questions here. Let's go through them, if I may, if that's okay, Danny.
Yeah, sure.
First of all, Patrick, thank you. You're welcome. And Andrew, thank you. I'm keeping going here. Oh, equipment, Christine wanted to know. Typically, here's the deal. When you normally image a star, how many pixels is that starlight falling on your camera? A handful, right? Full width, half maximum, whatever it is, you know, a handful of pixels. Now, if you take the same number of photons, right? You can't squeeze more photons out of that star through your telescope. So you take the same number of photons and now you spread them out. I'm trying to give you a visual example here. You spread them out over hundreds of pixels. Things get dimmer. You lose 5 or 6 magnitudes when you put a grating in the light path. Now that sounds like a lot, but there's a ton of interesting stars that are bright, and people spend years, in fact, sometimes decades, just looking at stars that you can look at with an 8-inch or 9-inch telescope. So the only restriction is typically you want to be 4 inches, better 6 inches in aperture, and low chromatic aberration, either an SCT or an APO, you know, ED glass, that kind of thing. Because we're dealing with color here, we can't have too much color distortion. It's a good question. So you typically need some tracking, but not great tracking, because we're not talking about, again, initially, and for a lot of what we do, a lot of people just don't bother stacking. They're not taking 15-minute exposure. They're doing, you know, on Vega or on, you know, any number of bright stars, you might be looking at 1 second, 10 second, 30-second exposure. So tracking's not critical. And a ding moment that I wanted to mention, and that is, I know you've got this, I was going to say cheese observatory or cheddar observatory, cheddar dark sky site. It's funny how the memory works. The great thing is spectroscopy is much less affected by urban light pollution. So instead of schlepping all the way out to cheddar, this is the kind of thing that you can often have fun and do a lot of interesting work right in your driveway in the city. Why is that? Because unlike visual, you know, when we're doing visual, we're looking for fine gradations and color balance, and we may be stacking hundreds of images and, you know, doing a lot of post-processing. We don't do any of that. You know, we're not doing, we want the photons the way they hit our sensor. So we're not doing all those post-processing steps. And furthermore, most of the time, all we're looking for are dips. We don't care if it's a deep dip or a deeper dip or a shallow dip. Yeah, you'd like a deep dip. You know, I'm the biggest dip of all. But so this is the kind of thing you can do in the city with relatively simple equipment. And let's see, Gerald has done some of this, so he's familiar with this kind of thing. And Oscar, I assume, is oh, there's Oscar. I see that Chuck changed the caption. That's great.
I know that there are a few astrophotographers in the chat. So some of us have full frame cameras. Some of us have cameras that have been modified to see in hydrogen alpha. Is that better, worse? Doesn't matter. Doesn't make a difference. I kind of assume that the size of the pixels might matter, since you mentioned with the equipment question that stars are tiny, so you want bigger pixels, and a full frame might not be that great. But how does that work?
That's a really, really excellent question, Danny. It's unfortunate the very first step in the spectroscopy is also the one that requires a technical discussion of the sort you're asking. But and on my site is a calculator,
right,
where you plug in your telescope, your aperture, your focal length, your camera pixel size, and it does all sorts of math in the background and tells you whether everything is sized to work well. So again, in terms of color versus mono, because that's been brought up here, and in fact, Gerald mentioned, and it's true that mono is going to be more sensitive, and also mono for certain scientific activities in spectroscopy is going to be scientifically more accurate. But a lot of us use color and just don't do that particular area of discussion. Now, another question was asked here: Betelgeuse versus Sirius. That's Andrew. And indeed, the way that astronomers, professionals tell star temperature is by the presence or absence of different spectral features. If you're not seeing a hydrogen bomber line, then it's not a type A star, because type A stars are right in the sweet spot temperature-wise, where you're going to see those lines very strongly. So in terms of looking at star types, there's so much that can be told. For example, Wolf-Rayet stars are going to have peaks because, again, they have this cooler outer shell that's being excited by the hot starlight going through. So there's a lot. I mean, that's the fun of it all. It's not just seeing dips and peaks, but going, now, why is that there? What does that tell me about the star? And that's where books like this, as well as the forum, and again, my manual, frankly, my software doesn't have a manual. It's got a getting started guide, and it's got, I think it's 45 3 or 4 minute how-to videos right now. The beauty of that is you don't have to, read a 500-page manual. So with all those tools, you don't, and I sort of been making a joke out of it that I'm a knuckle-dragging programmer, but again, you don't have to be an astrophysicist. Once you capture that spectrum of Vega or Sirius, and you see those bomber lines because it's a type A star, all of a sudden, next time you go to Wikipedia and read about type A stars or read about Vega, you're going to be able to go, oh yeah, I've seen that. I know what that looks like. That's a ka-ching moment. That's not even the first time I've used that. It's not even a ding moment. That's the money moment. That's what you're looking for, something that ties all of your experience together and then adds to it. God, it sounds wonderful when I say it that way. Yeah. What else?
So which would you recommend? Would you recommend just going out, pointing at any star and seeing what it is, or would you recommend looking for these main sequence stars, the O, B, A, F, G, K, M stars?
Right.
Those, and then looking at those, or just pointing?
That is a wonderful question. First of all, I wanted to tell you that I've been using that "Oh, be a fine girl, kiss me" acronym, and I was thinking it just because I'm a speaker in front of a group, and it was bothering me in the Me Too era. I was just thinking there has to be an alternate, and I have not been able to find any.
I am a big fan of KGB foam. That's the one that I usually use, and I had to write down here the OBAFGKM because that's the one that gets me for much of the same reason. But KGB foam is what's burnt into my brain. The downside is, of course, that OBA, it goes along with star temperature, so it's useful.
But I've got a new one for you. I've got a new one for you, Danny.
Okay.
And again, it's a little post-it on my monitor here. And there it is. It reads, it's not great, but it says, and if I could see the crowd, I keep mentioning that, and I mentioned it to Chuck and Danny. I know the club and some members had trouble getting into a Zoom meeting some time ago. And the YouTube format works fine. But I'd really encourage all of you to make the jump into a live Zoom meeting, because there's so much more social interaction in these days of isolation. And we're going to have them for some number of months, at least here going forward. It's great to be able to socialize. And again, you all, Danny and Chuck recognize that. So maybe you'll grit your teeth and try and make a Zoom of it again for everybody. But this says, "Okay, boomer, a fully green kilowatt matters."
Wow.
It's not memorable, but it is something that will work. So now, did I share? I shared my screen. So, oh my God, what am I seeing? What are you now seeing on my favorites? Oh no. Have I revealed anything? No, I think I'm safe here. This is sort of cool. This is a Kung Fu master. Anyway.
Oh, wow. All right.
What I wanted, you asked when you go out, what do you look at? And that, again, that's an obstacle. I feel that way. You know, I felt that way 10 years ago. It's like, okay, now I've seen Vega, now what? Well, on my page, on my site, here is a list of sample projects, some of which you've seen tonight, like
great.
this one.
Yeah.
You see those strong hydrogen lines on the type A star. But let's just scroll through here quickly, and you can see other examples of things that you can do, of projects you can do. So that's typically, and there's a broken link. I can't believe it. God, I'm glad I took a look at this. You can see this isn't something I show a lot of people online, but clearly I shouldn't be showing it tonight. Lots of examples of the kinds of things that you can see. So typically that's the way people progress. I wanted to show you this because it's sort of cool. If you're into variable stars, this is pretty neat. This was done by this guy Solachia with just, as you can see, a 4-inch refractor. It's a little video. I'm going to play it here. This is over just 2 hours. Watch how that spectrum changes. These deep dips, these deep absorption lines come into view, and the whole slope of this line changes, which means the temperature of that star is changing. And that's, so again, this could be a project that you could spend, months collecting data, figuring out how to collect it, then animating it. So there's lots of projects that you can do, and lots of interesting projects, both on our forum as well as in some of the books that are listed on my site. That's a good question. I'm glad you asked it. Let me stop sharing again. What else?
Good, yeah.
Another question.
Any other questions, guys? And well, as you were talking, I was writing a bunch of things down, and then you would answer it, and I would, cross it out.
Hey, Joe, I'm sorry the website's not mobile friendly. It should be. So it looks like I've got some other work to do on it. Gerald, yeah, the star composition changes as they get older. That looks like most of the questions people put up. Andrew, I'm happy to hear that you're interested in doing some of this. You've already heard or seen my contact information. Don't hesitate to reach out to me and ask questions. Anything else for me tonight?
Yeah, no, I thank you for joining us. And if you missed his link, it is rspec-astro.com. I will put that into chat here.
I was going to race you to type it in. I'll let you go for it. No, you go for it. You'll do it right. I'll mess it up. Thanks, Charles. I appreciate it. What's that wrench mean, by the way, next to their names?
That means that Chuck is a moderator. So,
okay. Good.
So if someone in chat gets mean or rowdy, and then he can delete their message or their message.
Makes sense. Well, good. Thank you again. By the way, I wanted to thank the club. I know you. I mentioned you. I know you do outreach. You're welcome, Bob and Real Ritz and Christine. I want to thank the people who are doing outreach. I think in many ways, this is my parting word, and you all know this, that it's a way we give back. We pay it forward, we pay it backward, and it's so nourishing. Even if we're not giving out and paying back, we're still nourishing ourselves by giving. So I'd encourage and thank you all for doing that, what you're doing. And as things continue to open up, I hope you'll get back to doing it because it is an important thing, especially these days. Thank you all again very much. Have a great night. You can see I love the topic. I'm sorry I didn't get the chance to meet you all, but maybe next year at Okie Text, we'll have that chance. I certainly hope so.
Yes, come to Okie Text, see our brand new building. You won't be in the tent. It'll be a nice air-conditioned place.
I'm glad I held out. That sounds great.
I mean, it's small silver linings there. But but hey, thank you so much again. We really appreciate it, and very true all of your words about outreach and just making sure that we find ways to connect with each other as best we can. So thank you for the talk, and thank you for joining us. And maybe we'll see you at Okitex.
Yeah, I want to, definitely. Let's make it happen.
Good.
All right. Thanks again, Danny.
Right.
Good night, everybody. Thanks, Marvin and Joel and all the rest. Good evening.
Thanks.
You're welcome.
Okay, guys. So I hope you enjoyed that talk from Tom. I know that I did. I always think that stuff is really cool. That spectroscopy and measuring the variable stars. If you were at Okitex last time that there was one, and there was that great talk about the discovery of Ultima Thule that used kind of a similar process and to measure the light that came from a star as this Oort cloud object passed in front of a star, and they use that. I just love that kind of stuff. So we are not done. We still have going to say thank you again, Tom, with my voice and in chat. Thank you so much. We do have a couple of other things to get to before we call it a night. I know there is snow in the forecast, but I hope that you guys can get outside and see the Geminids. That is a meteor shower that is peaking tomorrow, maybe through the early part of next week. So if you're going out to CRO tomorrow night or next Saturday night, take a lawn chair, sit outside, point yourself north, and try and catch some meteors. On the 21st is the closest conjunction of Jupiter and Saturn. They are going to be like right next to each other in the night sky, so be sure to look at that. If you don't know where either of those things are, well, hey, look here. In fact, if you want, I don't know which you would prefer. Do you want to see my face, or do you not want to see my face? And Patrick is not allowed to answer this question. So this is right now, right today. So we are going to switch to tomorrow, since we all are going to be out at CRO tomorrow night, because the weather will be perfect and bright and sunny and no wind, no snow. The lawn will look great. So this is tomorrow night about this time, about 8:30. And the Geminids are going to be in the constellation of Gemini. Let me bring this up for you guys so you can see this. Okay, so look in the northeast to the east, and this is about 9:30. I moved it ahead an hour. So just park yourself northeast, and just look up. Gemini is one of those constellations that when you see it once, you kind of can always see it. These two stars here are pretty visible. That's Castor and Pollux, and those are the heads of the two brothers. So Gemini is pretty easy to see. Don't really rely on this. It's going to be across a wide area. So just park yourself there, look north, northeast, and I think last year or 2 years ago, the last time they came around, I think we had a bunch of people go out to Cheddar Ranch. I remember Dave and Ida giving a little blurb or presentation about how they saw 50 an hour or something like that. So if you can get out and you can see the Geminids, it's probably the best meteor shower that you can see. If you miss them this year, they come around about once every 1.4 years. So most meteor showers come from comets. So comets are on an orbit around the sun, and as they break up, the pieces turn into meteors, and that's what we see. Well, the Geminids are actually kind of different. They're not a comet. They are an asteroid. Doesn't really matter. It's just kind of cool. So be sure and check that out. And if you miss it tomorrow night, then we'll just scroll through these next days, and you can see that it's gonna be in the sky until about the 17th. You see it disappears on the 18th, but if you can see it sometime between tomorrow and say the 14th or 15th, then you should go do that. So the next big thing that I want to talk about for this month is on the 21st will be the conjunction of Jupiter and Saturn. So I'm going to fast forward to the 21st. Now, you're going to need to get out pretty early, so right around sunset would be best. I've got it set at 5:30 here. Well, 5:27, and you can see that Saturn is starting to disappear. But if I zoom in, then you can really see that these two planets are really close to one another. Not quite touching, but very close. And I know the big question is probably, hey, can I see them both at the same time in my telescope? And the answer is probably. So this is the view through my 8-inch Dobsonian with a 9mm lens, and it looks like I can see them both. There's Saturn, and there's Jupiter, and there's some moons. So give that a shot. See if I've got my binoculars. Yeah. So with my binoculars, it might be a little okay. There's a slightly different pair. If I wanted to use my 71 millimeter with that 9mm lens, still kind of so. If you've got a Dobsonian, or you see one and you're out at Cheddar Ranch, take a look. You probably can get them both in the same eye piece. That will be really cool. And if not, it's still really cool to see these two planets just so close to one another. That is not going to occur again for 400 years or something. So be sure to check that out. The closest that they're going to get is on the 21st, but if I kind of go back in time a little bit, then you can see that they're pretty close to each other up until then, and then a bit after that as well. But you're going to start to lose them in that in that sunset sky. So those are the big things that you should look for in the next couple of weeks. I saw Andy in chat brought up Orion. You definitely should be looking for Orion. Orion is one of the best constellations in the sky, and very easy to find. Very, very pretty. You see it here, but without all of these lines and stuff, it still is very, very easy to find. It's got these 4 kind of stars that make a square that are kind of the upper body and the lower body, and then these 3 stars that make up the belt. So Orion has lots of great stuff in it. If you've got a telescope or if you've got binoculars, then you really need to make sure that you get a peek at the Orion net, as Tom was talking about in his talk. So I'll find. Yeah, so even with binoculars, it's going to look pretty good. So if you're from a dark spot, from the city, it's going to look like a smudge. So if you're out at Cheddar Ranch, be sure to do that. But knowing where Orion is, if you're new to astronomy, is going to help you out so much with finding other constellations and other objects. It's a great thing to know where it is in the sky, what's around it, what's inside of it, and once you know where Orion is, learning the rest of the sky becomes a lot easier, and there's just lots and lots of great stuff. Be sure to look at all these stars too, like Rigel, the variable star Rigel that Tom was talking about in his talk, or the red supergiant Betelgeuse star, or Bellatrix is a double star. It's the Amazon star. All these things are great to look at. So if you want some stuff to look at this month, look at the Geminids, look at the conjunction, and spend some time inside of Orion. So I'm gonna go back to my normal screen here. So it's about 8:30, so we've gone a little long. Santa Mike at the very first said I would tell you where you could get those cool Astronomy Club masks. So I'm gonna go into my plugs here really quick. We have a internet storefront on redbubble.com. You can go to redbubble.com/people/okcastroclub.com. I'm gonna paste that link into chat there. From there, you can get our logo or get the Okitex logo on all sorts of stuff. If you click the shop all products, and then you can scroll down and you can get it on t-shirts or tank tops or phone cases or pillows. I don't know why you'd want that, but that's there, as well as the masks. Mike didn't show this off in his video, but he also has the Okitex mask as well, and it's really cool. I saw that Andy is in chat. I know that we have some merchandise that you can get through Andy, most notably right now the club calendars. If there are any of those left, be sure to get with Andy and ask for one of those. Those are really, really cool and a great gift if you're still looking for Christmas presents for people. You can ask him a question at merch@okcastroclub.com if you are interested in something like that. If you are new and if you want to join our club, then we do have a way that you can pay online. If you go to okitex.org/shop, then you can buy a membership to our club for December through April, and then you will need to renew, but your first year is prorated, so I think it's $12 to join right now. Oh, and it looks like that Andy says that the calendars are sold out, but he still has some, or he's making some more decals and that sort of thing, and those are really cool too. Okay. So how do you get in touch with us outside of these live streams? Our official site is www.okcastroclub.com, on Facebook at facebook.com/okcastroclub, and on Instagram at instagram.com/okcac. As easy as Facebook may be, the easiest way to talk to us is on our website, okcastroclub.com, and you see our website here. And if you click on the discussion forum and register, it's free, and you can get news and information about what's going on at the club, or if you need a ride out to Cheddar Ranch, or an escort or a gear question, that's where you should go to find that. A personal plug, since my actual job with the Astronomy Club is making the newsletter on our website here. There is a link to the newsletter where you can go and you can scroll down and you can see a video from Chuck and some information about me and the club and what's going on, and these links to buy things are there. And then at the bottom here is kind of the same thing I just went through on Stellarium, in case I went too fast, and then you can see some screenshots about how to see the conjunction and about how to see the Geminids, and then some cool stuff about Orion. And there's also some links to some webinars and some YouTube videos and stuff that you can look at if you are looking for something to learn about or something to do, or you've got some free time. Okay, so that was it for the plug section. I really only have a couple more things to talk about with you guys. One is, so I like this YouTube format. I think it's easy and it gets us out to lots of people, and I can do fancy stuff like switch to Stellarium and have graphics and stuff. But Tom is right. When we have a speaker, we kind of lose that social aspect. So what I want to try to do, if there is interest, is maybe we every other week. So the second Friday of the month is the club meeting, and then between the club meetings, we just send out an email through Zoom or through Google Meet, and we just sit around and talk. And then whoever in the club wants to join by phone or by webcam, and we can just talk and catch up about what we've been doing and what we've been seeing and what we've been looking at. So if that sounds good for you guys, if there's some interest there, then I think that would be worth trying. And I do agree with Tom that we do kind of lose out on some of the social aspect, as we trade it off for the ease of use of YouTube for the social aspects of Zoom. So maybe we just do both. We keep the meetings on YouTube, and then in between meetings we do just a hangout on Zoom or on Google Meet, and just do that if that sounds good. And finally, I just want to thank you all. I know that this year has been weird, and we started to do these in April or May or June. I'm not sure. We didn't really know what we were doing. I didn't really know what I was doing. I knew that in theory I had the equipment to do these live streams, and we didn't really know what else to do. This was unprecedented that we couldn't meet each other in person. So we tried to kind of put something out there so that our members, so that you all could still feel like we existed and we could talk to you. So I'm just so grateful that all of you are watching this and have watched these. I see there's 30 or 40 people here still watching this, and the replays on YouTube get up to 200-300 views, and we've done these, and we've had some great speakers. We had Harry Magruder and that did that great talk about, and then Mike Madden, who was Santa Claus on video, and he gave a great talk, and John Blasey last month, and now Tom here. It's just so great that as wild as this year has been, that we've had these great speakers, and that we've had such great club members that have kind of dealt with us as we tried to make this work. And it looks like that we're going to be doing this at least for some part of 2021. So I just wanted to thank you all on behalf of the club, and especially on behalf of me personally. I know I'm probably not the first person that you would expect to host a live stream, but I really appreciate your patience and your watching and your questions and your chat, and I just think that's great, and I think this club is great. So with that said, I hope you all have Merry Christmas and great safe holidays, however you celebrate them. Please be safe, take care of yourself, and we will see you back here in 2021. So seems kind of abrupt, but I'll see you next month. Thanks again, everybody.